Hello, I was asked to cover problem 3.1.3 from the homework. This problem states, consider a point charge Q located at a distance d above an infinite conducting plate connected to ground. Find an expression for the attractive force that the plate makes over the charge. Find also the potential energy of the point charge. I always like to begin by writing out my goals. We have two of them for this problem. The first is to find the attractive force on the particle, which is indicated by boldface F. Boldface indicates vectors for this presentation. The second goal is to find the potential energy of the particle, indicated by W. In order to do this, we need an expression for the potential, V, that we can then use to find the work and the force. Now, if you recall, the problem called for an infinite conducting plate connected to ground. In cases where you have a conductor connected to ground, the method of images is normally a very good method to use to find your potential. So I use that here. I replace the infinite plate by an image of the charge indicated by negative Q, negative D, and then we use the superposition principle to add the potentials from both of the point charges together, and that gives us the total potential I have written to the left. A quick check of our boundary conditions shows that V does go to 0 at infinity, and it is also equal to 0 at the point where the plate would be in the center of the 2 point charges. Now that we have a V defined, we can find our electric field, which is negative the gradient of V, and we can also recall that the force is equal to our test charge Q times E. So we have it all set up to solve the problem for the force. For E, we find this expression where inside of the bracket, the first term is in the x hat direction, the second term in the y hat direction, the third term in the z hat direction. And similarly for the force, we have that expression times Q, indicated by the Q squared out in front, with the directions being x hat, y hat, and z hat for the 3 components. Now looking at the potential energy, we can see that the point needed to bring a charge big Q from infinity to the point R is given by W of R equal to Q V of R. And this corresponds to the potential energy of our particle when we take big Q to be equal to our point charge. Using the previously found potential, we can then determine W for this case, and we see W is now a function of x, y, and z, and it is given by this expression. And in conclusion, we can see that using the method of images, we can find a potential for this situation, and then use that to determine the force on the particle and also its potential energy. A quick comment, our use of the method of images to define a potential is valid, since due to the uniqueness theorem, this potential uniquely describes the situation since it satisfied the boundary conditions. We also found the force bold F and W as previously shown. And we can quickly observe that the force was found to be attractive and could be rewritten using the concepts of the method of images. So in the method of images, we just had the 2 point charges, and so here we have a force that is indicative of the force